We're going to have a look at nuclear shielding and atomic environments. So these are issues that come into play when we're looking at nucleon spin. And so if we have a nucleon with an upspin and a nucleon and an external magnetic field going upwards, then if this nucleon here absorbs a photon of light of the right frequency, it can become an excited nucleon by spinning against the magnetic field. And so the difference in energy between this upspinning nucleon and this downspinning nucleon, we will call delta E. So delta E is basically the energy of the photon that's absorbed, and it's the difference in energies between the high energy and low energy nucleon when they're placed in an external magnetic field. Now, obviously, delta E can't always be the same for any nucleon or any ever spinning, or any nucleus ever spinning. So here, rather than looking at nucleons now, we'll look at a nucleus with a net overall spin. So we'll say that this is a nucleus with a net overall spin, and this is a nucleus with a net overall spin as well. And they have a delta E between their low, and their high energy states. So delta E can't be the same for every different nucleus that we're dealing with. So delta E is going to change. This value of delta E is going to change as we change our conditions, and therefore the frequency of the photon of light that is absorbed will also change. So how does delta E change? Well, delta E depends on a couple of things. Delta E depends on the nucleus in question. So we know that only nuclei containing an odd number of nucleons are even viable candidates for having nucleon spin and a delta E. So the nucleus in question. So if we're only looking at the two examples, I guess, of nuclei containing odd numbers of nucleons are carbon-13 and standard hydrogen. So these are obviously going to absorb different energies as they realign themselves in an external magnetic field. They weigh different amounts, they've got different numbers of protons and electrons, there's more charge, they've got, there's a lot of different things between these two atoms and these two nuclei. And so for that reason, they're going to have different values for delta E when they're in an external magnetic field. The other thing that delta E depends on is the surrounding environment. So this is where the idea of nuclear shielding comes in. If we take a pretty simple molecule, here, let's say ethane. Actually, we'll make that propane. So if we've got a propane molecular structure here, like this, how does the surrounding environment affect things? Well, if we look at, let's make this hydrogen here the one that we focus on. The delta E for this, well, basically we've got a hydrogen atom here, and there are lots of other atoms close by. So we've got a carbon atom close by, we've got some hydrogen atoms around here that are close by, some more carbon and hydrogen over here. All of this stuff is very close to this hydrogen atom. And so all of these other atoms have their own protons and their own, electrons floating around in here. And what happens is that those electrons, so we know that spin is a magnetic phenomenon. Well, these electrons also have their own sort of spin or magnetic phenomenon in themselves. And what happens if we've got electrons very close by to this hydrogen atom is that these electrons, the magnetic field caused by these electrons, is going to sort of combine with the external magnetic field to change the conditions, to sort of change the conditions around this hydrogen atom. You could say that the magnetic field from these electrons is kind of sheltering or shielding this hydrogen atom from the external magnetic environment. So for example, if we've got this external magnetic environment, we might have an electron on this carbon atom that is actually got a bit of, that is forcing it back the other way. And so as a result, our net applied magnetic field, the magnetic field that this hydrogen experiences might be smaller than this. It might be only this big, a little bit smaller. And so this idea of shielding means that different hydrogen atoms, or atoms that are experiencing, the atoms that may have the same nucleus, so all these hydrogens all have the same nucleus, but atoms that are at the same time experiencing different amounts of nucleus shielding, they're experiencing different amounts of magnetism from surrounding electrons and other atoms, then they will absorb different amounts of energy. So if we look at these three hydrogens all have the same surrounding environment. They're all bonded to a carbon, which is bonded to another carbon, and which is then bonded to two hydrogens. Those conditions are the same for all three of these hydrogens. So we can say that these three hydrogens are in the same atomic environment and therefore experience the same amount of nucleus shielding, which means they will all absorb the same, they'll have the same delta E and absorb the same frequency of radio wave. If we look here, then these two hydrogens are going to experience different extents of nuclear shielding because they're in a different environment. They've got carbons with hydrogens on either side of them. And so that means that these hydrogens are going to be in different environments. If we move on to these hydrogens here, these hydrogens are in fact in an identical environment to these hydrogens. Because, again, if we say we were to flip this molecule within the page, then it would look exactly the same. If this went to the left, if we sort of flipped it like that around on its axis, then what we would get would be it's symmetrical. It would look the same if we flipped it. And so what that means is that these hydrogens are in the same environment as these hydrogens. They're bonded to a carbon, which is bonded to another carbon, which is bonded to two hydrogens. That was the same for these three hydrogens. What that means is that these three and these three are all in the same atomic environment. They've all got the exact same surroundings and therefore the same amount of nuclear shielding, the same delta E, and the same frequency of radio wave will be absorbed by them. So here we've got two different atomic environments, two different hydrogen environments, and therefore two frequencies of radio wave that will be absorbed by hydrogen atoms. So for every atomic environment within a molecule, a different frequency of radio wave will be absorbed. So let's do a few examples of how we want to count the number of atomic environments. So if we have more than one atomic environment, we're going to get more than one frequency of radio wave absorbed. So first, let's look at, we're going to look at two different types, two different very similar chemicals here. So this is what we refer to as 2-propanol or propan-2-ol. Then over here, we've got some 1-propanol or propan-1-ol. So these sound like they're very similar compounds. So we've got propan-2-ol and propan-1-ol. So how many hydrogen environments are there in each of these? Well, propan-2-ol, we can see that this is a symmetric molecule, and that means that these three hydrogens are all in the same atomic environment as these three hydrogens. Now, obviously, this hydrogen here is pretty unique. It's the only hydrogen that is bonded to the same carbon as the hydroxyl group, so we can say that that is in its own environment. Now, there's only one hydroxyl group, so that hydrogen in that hydroxyl group is also unique. So we've got three different hydrogen environments there. These six are all in the same environment because of the symmetric nature of this molecule. However, these two hydrogens are both in very unique circumstances, and so that we can say that they're in their own atomic environments. Now, if we look over at propan-1-ol, so we've got 3 environments there. If we look over at propan-1-ol, this is not a symmetric molecule, not left to right anyway. So if we were to say, we can say that these 3 hydrogens are all in the same environment, and there's no other hydrogens in the same environment because these are all bonded to the only carbon that has 3 hydrogens. None of the other carbons have 3 hydrogens, so that means that there are no other hydrogens in the same boat as these 3. They're the only group of 3. If we were to look for a second group, then we could go to say that these hydrogens are in the same group because they're the only ones bonded to a middle carbon. This carbon is the only carbon bonded to 2 other carbons, and so that makes this carbon unique, and therefore these hydrogens are different to all the other hydrogens. Now, if we look to this one, this carbon is the only carbon that's bonded to a hydroxyl group. So this carbon is also very unique. That means that the hydrogens bonded to it are also unique and in their own atomic environment. And again, this is the only hydroxyl group, which means the hydrogen in it is, again, unique. So it's in its own environment. So we've got 4 different atomic environments in this one. So these are chemically very similar substances. However, they have different numbers of atomic environments. Propan-2-ol will absorb 3 different frequencies of radio waves when it's due to nucleon spin, whereas propan-1-ol will absorb 4. So it's very important to be able to count and analyze the different atomic environments within a molecule, and this will prove very useful during NMR spectroscopy.